Okay, so this video is meant to walk you through collisions in 2D, and there isn't really anything that has changed going from one dimension to 2 dimensions. It just got a little bit more complicated in the fact that now you have to think about x direction and y direction. But essentially, momentum is conserved in every direction. So momentum is a vector quantity. So now you have to think about this idea that the initial x momentum is going to equal the final x momentum, and that the initial y momentum is going to equal the final y momentum. And so you can think about this through the lens of momentum or through the lens of velocity, but regardless, you have to think about it in terms of the vector nature of this. So our problem-solving method is going to stay the same in that we're still going to draw out before and after pictures, but now we're just going to insert one step. When we do our before and after pictures, we need to break things up into components and think about the x and y nature of our velocities or our momentums. And then we find what our final momentums are, and same, we're going to look at the vector nature of it, and we would just set them equal to each other, okay? So in terms of like the strategy, the only thing is we have to add into the step of breaking things up into components in order to truly analyze the equation, okay? So we're going to go 2 examples of momentum or collisions rather, in 2 dimensions. The first one is a kind of straightforward inelastic or completely inelastic collision. So you've got 2 ice skaters collide in a completely inelastic collision. The first ice skater has a mass of 35 kilograms. So let's just kind of write that out. That's my mass 1, and is originally moving east with a velocity of 6.2, so that's my V1 initial. The second ice skater has a mass of 22 kilograms, so that's going to be my mass 2, and is originally moving north with a velocity of 7.8, so that's my V2 initial. What is the final velocity of the pair, magnitude and direction? So again, we're going to do our steps. We're going to draw this out, and we're going to think about the vector nature of this. So in my before, and I'm not super good at drawing people, let alone people ice skating, so I'm going to reduce them down to a dot. So here is my mass 1, and it has this initial velocity in this direction. And then here is my mass 2, and it has an initial velocity in this direction. And then, oh, hold on. I want to just give myself a little more space. I only have so much whiteboard to work with. Okay, so there's my mass 1, my mass 2. So mass 1 had V1 initial, V2 initial, and then afterwards, they become like a supermass. Mass 1 plus mass 2. And if we had x momentum to begin with, we still have to have x momentum. If we had y momentum to begin with, we still have to have y momentum. So they are going to move off in this direction. Some v final at some angle, okay? So this is kind of looking at the vector nature. Like this is like a v final x, and this would be a v final y, okay? So out of my drawings, I'm going to get some equations now for momentum. So this is saying initially, in my x direction, I just have mass 1 and v1 initial. And for my y direction, initially, I just have mass 2 times v2 initial. And then afterwards, my final momentum in the x direction is this like combined mass times this v final x. And here, and afterwards, this is going to be my combined mass times v final y, okay? And so I can set these equal to each other, right? So I have all the numbers. I can find v final x and v final y. So this would just be 35 times initial velocity of this guy is 6.2 equals my total mass of 35 plus 22 times v final x, similar process for my y, but I'm going to use my m2, which is 22, times the velocity, which is 7.8, times the initial velocity. No, golly, that is my initial velocity. This is my initial momentum. That's going to equal now my total mass, so 35 plus 22 times v final y. Okay, so figure out what v final x is, what v final y is, pause the video, do the right thing. I don't even know what it is, because I can calculate it. Okay, so my v final x, I get 3.99 meters per second, and then for my v final y, hopefully it won't take me as long, I get 3.01 meters per second, and that's the components. So to figure out the actual total, you would just use geometry and Pythagorean theorem, because the x is this 3.01, the y, I'm a liar, the x is 3.99, the y is 3.01, so you'd Pythag to find this resultant, and then you'd use inverse something, sine, cosine, tangent, to figure out the angle. So I get, this little rinky-dinky calculator. I get 4.99 meters per second. And my angle, I get, 37 degrees. Okay. So that's a case where you have a completely inelastic collision and they stick together. Let's look at a case that's a little bit more complicated, where they don't stick together. So in this one, it says a proton with a speed of 500 meters per second collides with another proton at rest. The projectile proton is scattered 60 degrees from its initial direction. The target proton scatters 90 degrees from the projectile. Proton, what are their speeds after collision? So there's a lot of protons. So kind of before and after picture. So before, I have proton 1 moving super fast, and proton 2 is just doing nothing. So its initial velocity is 0. And then afterwards, we're told that the projectile proton, so that's the one that's moving first, scatters 60 degrees from its initial position or direction. So if it was going kind of horizontal in my picture, 60 degrees is going to kind of move it up. So there's my mass 1, or I could have it move down, but I'm just going to pick up. There's my V1 final, 60 degrees. And I'm told that my target proton, mass 2, scatters 90 degrees from that one. So if I kind of think about this in terms of this guy is going to scatter like that. Okay, so they both have x and y velocities afterwards. Okay, so if I were to think about the x direction, and I'm going to kind of skip some steps here because you've seen examples of conservation momentum. I'm going to set the initial equal to the final. I'm going to set the initial x momentum equal to the final x momentum. So my initial x momentum is this m1 v1 initial. Okay. My final x momentum is the momentum of mass 1 plus the momentum of mass 2. Okay. So this is going to be m1 v1 fx plus mass 2 v2 fx. Okay, so that's looking at the component nature of the velocity. Now, we know that we could represent that in terms of the angle. So, and I'm just going to get a number for this. Actually, my masses are all the same. They're all protons. So m1 is equal to m2. So I could actually cancel out all my masses. Convenient. So this says 500 is equal to V1 I'm going to go V1 final times the cosine of 60 plus V2 final times the cosine of 30. Okay, so what I did was, instead of looking at the x component, like in terms of the variable, I said, well, I know, I'm going to draw this, I know that if this is V1 final, and if this is V1 final x, this is just, I could find this because this is the cosine theta side of this. This is the adjacent side. So V1 final x is just V1 final times the cosine of theta. Okay, so that's the substitution I just done right here. Okay, now I'm going to think about the y direction. What's easy is I have no momentum to begin with for my y direction at 0. But I do have mass 1 V1 final y minus mass 2 V2 final y. And the reason I'm subtracting these is because V1 final y is going up, V2 final y is going down. So I'm going to subtract them. I'm going to do the same thing I just did here, put it in terms of a trig function, and in this case it'll be the sine. So this is going to say, and actually, if 0 is equal to this minus this, these two are just actually equal to each other. And the masses cancel out. Whew. So we can get this relationship that essentially says V1 final y is going to equal V2 final y. But let's put this in terms of the sine. So V1 final sine of 60 is equal to V2 final sine of 30. Okay. We've got a system of equations. This equation has a V1 final and a V2 final. This equation has a V1 final and a V2 final. So we're going to substitute. So it's probably easiest to just solve for one of these, and we'll just divide both sides by sine 30. So we get this relationship that says V2 final, and I'm actually going to calculate that out, like what the sine of 60 divided by the sine of 60 divided by the sine of 30. Oh, golly. Sine 60 divided by sine 30. I get 1.73. So 1.73 V1 final. So that's like my relationship for V2 final is 1.73 times V1 final. And we can go ahead and plug that in here. So I get this 500 is equal to, and let's actually get rid of this cosine 60. Oh golly, that's just 0.5. 0.5 V1 final plus, instead of V2 final, I've got this relationship. I'm taking this relationship here, and I'm plugging it in there. So I've got 1.73 V1 final times the cosine of 30. And so now we can just algebraically manipulate this. Like, what is 1.73 times the cosine of 30? 1.73. And I'm gonna erase this because I've run out of room, as always. I get here that 1.73 times cosine of 30 is 1.498 V1 final, and then this is 0.5 V1 final equals 500. So now you can combine your terms and solve for your V1 final, and you get that V1 final is approximately 250 meters per second. And now that you know V1 final, you can go back into that relationship that says V2 final equals 1.73 V1 final to figure out V2 final, and you should get that V2 final comes out to be 433.01 meters per second. Okay? So conservation of momentum in 2 dimensions isn't necessarily more complicated in terms of like what you have to do. It's just more complicated in the fact that you have to think about it in the x direction and the y direction separately. Okay?